Before we start our next lesson on binomial probability models, I want to review permutations and combinations from earlier courses. In a permutation, order is very important. Like the order 524 is completely different than 245, whereas in combinations, order doesn't matter. So think of locker combinations. Locker combinations are named wrong. Combinations are usually three numbers, like for might be 0, 5, and then 27 might open your locker. Well, if you put it in any other order, it's not going to open, so it's actually a locker permutation, not a combination. Consider this first scenario. There are 5 students running for class president and 5 vice president. How many ways can these... So let's identify what each scenario is. There are 5 students running for class president and vice president. How many ways can they fill these offices? Well, I get to choose a president and I get to choose a vice president. So order matters, whether you're president or vice president. So I think I have 5 students that can run for president, which would leave 4 remaining to run for vice president because 1 gets selected to be president. Multiply this together and I get 20. In notation, this is a permutation. From 5 students, I'm choosing 2. You'll see it written like this. You'll also see it written like this. From 5, choose 2. There is a calculator function that will calculate that for you. I will show you that momentarily. There are 5 students volunteering to serve on a spring fling committee. How many ways can 2 students be selected from 5 to serve on the committee? So since we're just getting 2 kids to serve on a committee, the order doesn't matter. So this is a combination. From 5, I'm picking 2 kids. Also written like this, from 5, choose 2 as subscripts. Okay, what is this equal to? Well, it's equal to a permutation of the same thing. So how we did 5 times 4 for the 2 positions. But we've got repeats, so what we do is we take our second number, divide by that factorial. Reminder of what factorial is. That's the same as, in this scenario, 2 times 1, which is 2. So I'd have 20 over 2, which is there are 10 combinations. Another reminder on factorial, if you had 12 factorial, that would be like 12 times 11 times 10 times 9, all the way down to 2 times 1. Okay, so sequentially in descending order. On the calculator, we're going to be using combinations a lot in our next lesson. So to do combinations on your graphing calculator, take a second and try it. You're going to hit math, you'll arrow over to probability and choose option 3, and you'll see it says C and then N and R. So you're going to just input that you're finding combination from 5, choose 2, and the calculator will output 10 for you. So combinations are going to be used in binomial models. So let's look at what conditions need to be true in order to apply a binomial model to it. So your probability has to be as either a success or a failure. Okay, it can't be 3 different options, it has to be just 2, success or failure. Your events must be independent. So if we are saying we're rolling a die and we want to know what's the probability that it ends up being a 2, okay, so it's either you get a 2 or you don't get a 2. Don't think of it like a 3, a 4, a 5, all those different options. So you either get it or you don't. So in this scenario, your probability of a success would be 1/6. A failure would be 5/6. And then independent, okay, so the first roll has to be independent of the second. If independence is violated, which sometimes occurs like in real life scenarios where you're sampling without replacement, like maybe you're sampling things off an assembly line, so you start pulling off a Skittle to test things, to taste it or whatever. If you're pulling things off the assembly line, you've altered the sample space, so now the probability that like the next one you choose is red would be altered. So if you have sampling without replacement, it's okay to continue if the sample you're choosing is less than 10% of the population. That's known as the 10% condition. So it's okay to proceed. You'll also see this written as long as N, our sample size here, is less than 1/10 of our population. N means we have a fixed number of trials, and then S, the success the probability of getting a success stays the same, like it's constant, it's not going to change. So this acronym BINS, think binomial BINS, will help you check your conditions to see if it's appropriate to use the binomial model. Okay? In the binomial model, we get to use it in this special scenario if we're trying to find the number of x successes and a fixed number of n trials. So x is going to represent number of successes, whereas n is the number of trials, and p is the probability of a success. You do not need to memorize the formula for a binomial model. It is given to you on the formula sheet. Here's a screenshot of the formula. Looks a little complicated, but it's really not bad. I'm going to actually logically help you think through it. Here is our mean, our expected value, and our standard deviation of the actual distribution. And we'll look at the actual distribution in the next lesson. Here we're just going to practice using this to calculate different probabilities. So here's an example from your text. Genetics says that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let x equal the number of children with type O blood. Find the probability that x is equal to 3, and then interpret this value. So what is this indicating? Well, we were looking for what's the probability of 3 out of a fixed number of 5 children, which is where my brain goes, oh, I could potentially use the binomial distribution here. So I need to check and make sure that my conditions are met. Is it binary? Well, yes. A success is type O blood, and a failure would be not having type O blood. Is it independent? Well, yes, we are told in the scenario that one child's blood type is independent of another. N, is there a fixed number of trials? Yes, N is equal to 5. And is the probability of a success the same? Well, yes, the probability of a success is 0.25, stays the same for S, stays the same. So my conditions are met, so now I know I can use a binomial distribution. Well, I'm going to help you just kind of think this through. So I think the easiest scenario would be that the first 3 children of the 5 would have type O blood, right? And then the last 2 not. Well, that would mean that probability would be equal to 0.25 3 times, right? Because there's 3 kids with O blood, and then 2 kids, 0.75 times itself twice would be 0.75 squared. But that's just one possible combination for how this could play out. I could have it where the firstborn child would be O positive, the second-born was not, third was, etc. So there's a lot of different combinations. So what I'm going to have to do here is multiply it by the number of combinations. Well, combination from 5, choose, not 4, choosing 3 kids. And I'm going to write this in proper notation. So I'm looking for the probability that my random variable, which is x, and they told me that x is the number of children with type O blood, is equal to 3. Now notice I didn't put the C this time, just because when you look at the formula, you'll see that they don't do that. So on the calculator, I'm going to figure out a combination of from 5 choose 3, and that's 10. And then I'll just type in times 0.25 to the third and 0.75 squared. It gives me a probability of 0.08789. Now, I want you to just see how that was by logical reasoning, but we could just use the formula. So I've just placed the formula from the formula sheet on my screen. And let's see here. We can just substitute in. So from n, choose x, which is what I have. From 5, choose 3. P is the probability of a success to the x power. So 0.25 to the third times the complement of that, which would be your probability of a failure, 0.75 to subtract the n minus the x. So this minus this would be squared. I just think it's a lot more logical to kind of think through it, but of course it's right here if you need it. No need to memorize. So when it says interpret, this means that there's about a 9% probability that exactly 3 of the 5 children have type O blood. Now we're going to use that same scenario, but a different question. Should the parents be surprised if more than 3 of their children have type O blood? So if we just think about, okay, first of all, I don't need to go through bins again because it's the same scenario. I already know that a binomial model distribution here is appropriate. So if you have 5 children, 0 of them could have type O, 1, 2, 3, all the way up to all 5 of them. So that's how this could play out. So we're saying, what's the probability, if we're saying should they be surprised, let's calculate that probability. If more than 3 would be 4 or 5 of the children. So I'm going to write this as the probability that my random variable is greater than 3 is the same as probability of the random variable equal to 4 plus the probability of the random variable equal to 5. All right, so I'm going to find each of these, the 4 and the 5, and add them together. So 4 children having type O blood would be 0.25 to the 4th, and 1 failure. So that would be 0.75, didn't mean to write a 1 there, just said 1, so I wrote it, to the 1st power, because you've got 5 children total. But then we got to think the combinations. So that would be combinations. We would have from 5 kids, we're seeing how many ways, 4 of them. We could take groups of 4. But then I need to find probability that my random variable equals 5. So again, same scenario, from 5, I'm choosing all 5 of them to have type O blood. So it'd be 0.25 to the 5th power times 0.75 to the 0 power, which hopefully you remember from earlier courses that this right there is actually 1. All right, so from 5, choose 4. It's going to be 5. Again, you can just do that on the calculator. From 5, choose 5. Well, there's only one combination where that would happen, times 0.25 to the 5th. Okay, so if you type this in your calculator, you get 0.01563. And if you think about, is that unusual? Well, yeah, that's less than 5%. Remember, we kind of use our 5% as our cutoff. So would the parents be surprised if more than 3, meaning all 4 or 5 of them, have type O blood? Yeah, I would think that they would be surprised. Lastly, I just want to tell you that there is a function on your calculator that will help you do this. It's hidden in distributions, same place normal CDF was. If you arrow up, you'll see Binomial PDF. It's option A. So if you pick Binomialpdf, the P equals 0.25 and X equals 4. Notice I'm putting in my parameters for the calculator talk, and I hit enter. That's going to give me just for 4 children having type O blood type. If I add that, okay, to Binomialpdf, N equals to 5, P equals 0.25, and X equals 5. If I add those two, I can do it all kind of on one screen and hit enter. You'll see you get the same value, 0.01563. So just so you realize what's acceptable on the AP exam is you can use this calculator talk, but you make sure that you first show what it is you're finding, where probability that X was greater than 3 is equal to the probability of X is equal to 4 plus the probability of X equal to 5. And you may use your calculator talk. It still is necessary to address your conditions, though, the bins. You can't just jump right into calculator talk. And then lastly, the one other calculator function is Binomialcdf, which gives you the cumulative distribution of your density function. So imagine, let me change that to CDF. Okay, cumulative. So what that does is it adds the probabilities together. So think you could have 0, 1, 2, 3, up through 5 kids. So if I do It's going to add from left to right. So if I want to know the chance of 4 or 5, what I could do is do the cumulative for up to 3 and subtract it from 1. So this would be equivalent to 1 minus binom CDF with n equal to 5, p equal to 0.25, and x equal to 3. Because mathematically what I'm saying is the probability that x is greater than 3 is equal to 1 minus the probability of x less than or equal to 3. Okay, so try that on your calculator and you'll see that you get the same thing. Ask questions in class to help clarify, because I know that was very quick.